Using the principle of mathematical induction, we want to prove that the sum of perfect q's from 1 to an unknown number n is equal to n times n plus 1 over 2 square. This will work out easily if we follow certain steps. The first step is to test with the first few values of n. A quick way to check if the expression is correctly represented. Secondly, make a substitute of m with n on the left and the right-hand side of the equation. This works as a support for the third step in carrying out the proof. Lastly, make a substitute of m plus 1 with n on the left-hand side of the equation only. Then prove the expected outcome on the right-hand side. The expected outcome is increased by 1 on the right-hand side. Let us see how it works. Starting from the first step, when n equals 1, we see that it is valid, and both the left-hand side and the right-hand side give a singular result, 1. The same goes for the second number to be tested. At n equals 2, the right-hand side becomes 1 raised to the power of 3 plus 2 raised to the power of 3, which sum up to 9. For the left-hand side, direct substitution yields 9. This is also true for right-hand side. For a substitute of 3, the left-hand side becomes 1 raised to the power of 3 plus 2 raised to the power of 3 plus 3 raised to the power of 3, which gives 36 as well as the right-hand side. The first step in the proof ends here, while we move on to the second step. The second step is to make a substitute of m with n on the left and the right-hand side of the equation. With this, we can simplify the third step and embed this result. Now, the next step to take is to make a substitute of m plus 1 with n on the left-hand side only, then manipulate to derive a corresponding expression for the right-hand side. That is the third step. Now, we want to simplify this expression, being interpreted as the sum of all perfect q's from 1 to m plus 1. According to the rule of summation, we can sever out the last term, then take the sum to the last term minus 1. All in the sake to make a big part of the expression easily take a substitute from the second step. Since this is exactly like the expression we have in the second step, we take a substitute of this with the right-hand side of the equation in the second step. Our new expression becomes m times m plus 1 over 2 square plus m plus 1 raised to the power of 3. From here, we factorize our expression. Factor out m plus 1 square. So, the following expression emerges. Take the LCM of the expression in the bracket and convert the expression to a single fraction. Follow the steps carefully. This gives a result of m plus 1 times m plus 2 over 2 square. With this result, we can conclude that the expression with which we started with is correct. We tested for m plus 1, so the expected result should also has an increase in each position of m by 1. Thus, the expression is true by the principle of mathematical induction. Here is another example. We want to prove the famous geometric series formula for nth term. Our method of solution remains the same. As courtesy demands, we check for some values. Take n equals 0, n equals 1, and n equals 2 respectively. The comparison of the left-hand side and the right-hand side in each case shows that it is valid for the values. You can further simplify the left-hand side in each cases to confirm. The first step ends here. The step number 2 is to assume that it is also true for a constant m also. Then we write it out. And lastly, we want to prove that it is also valid for m plus 1, starting from the left-hand side. By substituting m plus 1 with n, we have the following expression. Again, we need to consider the rule of summation and separate the last term from the compound. The following expression pops up. Don't forget that we already have the answer to this in step 2. So, all we just need to do is to substitute it and simplify our result. This leads to 1 minus x raised to the power of m plus 1 over 1 minus x plus x raised to the power of m plus 1. Convert the expression to a single fraction. Then we simplify the result. We see that x raised to the power of m plus 1 cancels out. And our result becomes 1 minus x raised to the power of m plus 2 over 1 minus x. This is the expected answer, since m increased by 1. Thus, the proof is complete by the principle of mathematical induction.
I'm gonna stand up for what I stand for. Fight till finish and win the war. I'm gonna keep on